Hello everyone, welcome to MLAS 700, Advanced Cybernetic Systems Development, Learning Activity 7. And in our lecture series for this week, we will be focused on jumping into machine learning frameworks. High level, what algorithms are out there and how is machine learning really structured. And then from there we'll dive into a little bit of the details of each different area. But then the other thing that we'll do is talk about machine learning development frameworks. In other words, okay, that's great. You've showed me what machine learning is at a high level, but then how do we actually do it? And then what are we going to use? And as we move along in the lecture portion of the course, we'll be focused on learning, of course, the concepts around machine learning, and then the labs will kind of catch up and coincide with what we're learning from the lectures, and then the labs will catch up as we move along to some of the concepts that we're going to be implementing. Of course, we have to bring you up to speed on what bare metal programming is. So we'll be doing some basic projects in our labs this week, and then we'll slowly work up to more advanced projects in our labs, and then get ourselves into a good position to be able to do some actual machine learning labs towards the tail end of the course. Okay, so let's jump into the second slide here. So what is machine learning, and what are the major categories of machine learning? Well, there's three big ones, with a fourth one that we'll talk about. It's actually something that we teach in our undergrad. As each one of these we teach in their undergrad, in their specialization. In other words, we have a course in supervised learning, a course in unsupervised, a whole course in reinforcement, and then we have another course on deep learning. And so we do a much deeper treatment of it there, but we get more into the theoretical aspects of it and then work our way into applications. In this course, we're going to be focused on doing a little bit of theory, but not too heavy. We're gonna go, because we don't have a lot of time. In theory, of course, is stuff that you can learn on your own, but the application is harder. So that's something that we're going to focus on in this course. So first up, we have unsupervised learning. So unsupervised learning primarily falls in two buckets, which is dimensionality reduction and clustering. When we talk about the dimensionality reduction, we're talking about taking high data that has high dimensionality and reducing it into two or three. We reduce it into 2 or 3 dimensions, and it's really a neat. The algorithm is pretty cool, or the algorithms, I should say, are pretty cool, that operate in the dimensionality reduction space. And what you're trying to do is a lot of times when you're doing dimensionality reduction, you're looking for patterns, but you're not looking for patterns in data based on training data. So we call that typically clustering. So these work together hand in hand, dimensionality reduction and clustering. Usually are features that are outputs in unsupervised learning, that work hand in hand, and unsupervised learning does not leverage any pre-labeled data or pre-trained models. In other words, we tokenize the data, if it's alphanumeric, we tokenize it, and then we do some math on it to see if we can find some patterns in the vectorized data. That's unsupervised learning. Supervised learning is what we call classification and regression. Regression is a fancy word for prediction. Classification is another word for clustering, but the difference between clustering and classification is clustering is unsupervised categorization of patterns within the data. Classification is similar, but the difference is it uses training data to find categorizations within the data. So typically within a classification exercise, if, for example, let's say I want to classify a cat versus a dog. So I'll create a neural network, and then in that neural network, I'll feed that neural network lots of different pre-labeled data that I feed to the algorithm to say, hey, this is images of cats and these are images of dogs, so that when I run an unknown image in front of the algorithm, it can then predict whether it is a dog or a cat, and that's called a predictive classification or a predictive classifier. That's very different from a clustering where there is no supervised data for it to go. There's no pre-trained, pre-labeled data in a clustering scenario. You'll just get a pattern for this is pattern for dog, this is pattern for cat, but it's not based on any type of data in training. So there you can, as you can imagine, there's ups and downs. There's of course there's a single step process in clustering, and usually clustering algorithms are super fast. And because it's a single step process, it usually runs pretty quick. Classification is a multi-step process. Usually it's ensemble methods and or neural networks, and it's a multi-step process to get to a classification. Usually takes longer to do a classification task, but as you can imagine, you'll have a higher precision, a higher accuracy with pre-trained pre-labeled, pre-trained models that give you a better classification rate. Whereas in clustering, you're probably not going to get as high as a hit rate when you're doing data categorization. So moving on to regression, you've got a lot of different. There's a lot of different predictive algorithms. There's ARIMA methods. There's regression methods. There's a lot of different predictive methods for what happens next. As you saw in my last lecture, you can forecast what's going to happen next based on just a moving average, which is a typical, which is a very basic algorithm. But in a regression, there's actually linear algebra that's involved, and so we follow a line of best fit, and then there can be actually polynomial regressions where I follow a wavy line, not necessarily a straight, simple linear regression. I can have a polynomial regression as it relates to that. Also, there's different types of regressions that use different statistical mechanisms. There's thousands of different ones, but there's usually typically two different types. There's a robust, and then there's regular regressions, and then there's what's called robust regressions. And but then there's also logistic regression and so on and so forth. But I'm talking about the statistics, the underlying statistics. And a robust regression uses a median and not a mean. Most regressions use a mean average, not a median average. And so, or I should say average is the wrong word. A statistician would give me a hard time about the way I just described that. But if I'm looking for the middle point of a data set, you typically have two ways to do that. A mean or a median. And so a median usually describes is usually in the machine learning world, we would call that a robust regression. And then, as you can imagine, there are pros and cons to that. As it relates to your learning reflection, I would like for you to think on this for your next learning reflection paper. What are the ramifications between a regression that uses a median versus a regression that uses a mean? And so I want you to do a little research, look into that, because it has to do with outliers. I'll just give you a little hint. It has to do with how outliers are managed. So that's what regressions are. Regressions are used for predictions and forecasts. Last, we have reinforcement learning. So in reinforcement learning, we talked about that in our lecture last week, and reinforcement learning has to do with it's Markov decision chains, and those use a reinforcement process to navigate a decision tree, a decision flow, so to speak. and a reinforcement through that flow. And it's more, and so none of these are better than others. So let me be clear on that. So reinforcements used for certain situations. Principle, if you've got a certain task where you're just looking at pure patterns and data, then principal component analysis for clustering and dimensionality reduction is your best way to go. If you're looking for predicting a future event, like let's say estimating if a game is going to go one way or another, like a soccer game, let's say, then or a baseball game, then that would be a supervised learning task using a regression. And it could be a predictive classification, like in other words, the classification of a win versus a loss. That is a classification, right? The loss of winning, not winning, that's a classification, but it is a predictive classification. So that's something where that might be a logistic regression, right, on the output. So there's just different things, different algorithms. If I've got weather predictions, it's going to be multivariate regression, or it could be even more complicated, like an ensemble method, like a random forest. So there's just a lot of different ways to go about it. There's just no single way, and in some cases, you'll have all three of these: unsupervised, supervised, and reinforcement in a multimodal model of machine learning. I will say I don't have it on here because I do want to have a separate conversation around neural networks. But the deep learning is when we're starting to use artificial neural networks. So when we talk about large language models, which is what you're going to cover in MLAS 800, we're going to do a deep dive in deep learning on that. So I don't want to spend too much time in this course talking about it, except to give you a heads up that we will be doing deep learning, which is another machine learning method using neural networks, but we're going to be using large language models, and again, we'll cover that in MLAS 800. Some of you may have already covered that. Great. If you went through that, then you're already up to speed on that. So let's jump into supervised learning. So supervised learning is, excuse me, where I can use I can do image classification, or I can do pattern recognition, again using a model that has pre-trained data that can tell me whether something's good or bad. In this case, on the left, I can use a classification, and then I can do a predictive classification to say, hey, based on the data I've seen in the back end, and I can produce a predictive output to estimate. Estimate's probably the better word, but to estimate is what I'm looking at, something that is disease or something that is healthy, as an example. Or I could say, like I used earlier in a baseball game, I can predict whether I'm going to have a win or a loss. So that's a classification. Now, a regression is a prediction, and instead of the line being used, so when I have this line here, this is called a hyperplane in a classification scenario, but in a regression scenario, it's a line of best fit. So in a regression situation, I'm saying, hey, if I've got something where as a particular gene, or as something, in this case, as something moves along, this is a survivor model, I can estimate, I can say, hey, this is gonna predict life expectancy, or I can say this is going to predict geography, like where potentially is a storm going to hit, right? Or I can predict population growth, or I can predict whether someone's going to purchase a product, right? A marketing forecast. So that's what a regression does. Is it says, hey, I'm going to plot a line here, and then if I put something out here, further out here, then I can estimate that it's going to be up here. So I can predict that. Let's say this is so if this is years, right? I can predict, like, oh, that if given some event over here, some category of something occurring out here that's off the graph, I can estimate the year based on where this plots, right? Based on what this plotted series, this scatter plot is showing, and that's a regression. Okay, so unsupervised learning. There's there's dimensionality reduction, which is I'm going to use. This is a pretty common one. This is a principal component analysis of what's called the iris data set, where I have the length width of a petal, the sepal length width, and then I create what's called an eigenvalues, and these are eigenpairs. And what it does is it takes those four values, 1, 2, 3, 4, sepal length, sepal width, petal length, and petal width, and then it reduces them down into 2 dimensions. And then I can do that, and then I get categorizations. I vectorize that information, and in this case, these are already numerical values, so I don't have to vectorize the data. When I say vectorize, I'm usually taking an alpha category and converting that into a number. So that's what I mean when I say tokenization. I'm sorry, vectorization. I'm getting my natural language processing wires crossed. So in vectorization. So, but in dimensional reduction, what I do is I take those 4 and I convert them into two dimensions, and then I plot those eigenpairs. So if you want to learn more about that, it's definitely that's a deeper dive into principal component analysis, and we'll maybe cover some of that as we move along, but we'll see if we'll see what happens. Next up, we have clustering. So in a clustering scenario, on the output of the dimensionally reduced data set, I then can create a cluster. And in that cluster, I can use that clustering. So dimensionality reducers, in this case for PCA, I have a dimensionality reducer that is used for the clustering. And then there's other types of dimensionality reducers. There's dbScan. That's the algorithm. So you have PCA, you have dbScan, you have t-SNE, which is t-stochastic nearest embedding. And so that's a newer, dbScan and t-SNE are newer algorithms. PCA has been around as an algorithm for 100 years now, 110 years. And it's been developed. A lot of the math for this has been developed over the last hundreds of years. But PCA is still, to this day, a very, very relevant machine learning, clustering, dimensionality reducer machine learning algorithm that was developed back in the early 1900s. So that's kind of some fun trivia. t-SNE is a lot more time intensive calculation wise. It's very, very time intensive. So when you run t-SNE, it usually takes a lot longer to do the same types of clustering output that PCA would do. But t-SNE actually gives you a lot more. We can add a 3-dimensional or a 3D component to t-SNE, which is something that you can't always do with PCA, which is nice. So I can in other words, I can reduce from high dimension data sets down to 3 dimensions instead of 2 dimensions, and t-SNE gives you that capability. dbScan is pretty powerful as well. It's a newer one, pretty quick too, from a time complexity perspective. It's very useful. Okay, moving on to reinforcement learning. So in reinforcement learning, if you look through this is very similar to the example that I showed you last week in terms of reinforcing the predictive outcome of what happens next. So that's exactly what a reinforcement learning model does, except it usually uses what's called Markov decision chains or Markov decision process within each chain. So each iteration is its own change and changes the state of the system. So you can think of these as like a state, kind of working back to your design and dynamics where you have loop systems, cybernetics. This is very cybernetic-y, right? This is very, I have a loop model that I create for my system dynamics, right? And then what I can do is I can reinforce using a Markov decision process my system dynamics. So in other words, when you were in design and dynamics and you were creating models, you were literally creating a real-time Markov decision process that you could see moving, and you could take this, what you see here, put that into, I think we used Loopy, use Loopy and then run it quickly, and then you can actually see what the output of this looks like on each pass, right? And you can influence it by like reinforcing, like, okay, I'm sleepy, I hit snooze, then I wake up, and then if I wake up, I call in sick, and then I go back to bed, and then if I keep reinforcing this model, I can actually reinforce myself into this loop to the point where I never go to work, as an example, right? So and then I can keep reading Twitter, and I can reinforce my Twitter reading, and then I can just stay in bed and just kind of stay in this model of going to bed. So there's a really good example here of what a Markov decision process looks like. And I highly encourage you, if for extra credit, you can take this Markov decision process and then go and run it into Loopy and show me that you recreated this, and then give me your estimation on like what you learned from it, because that would be a visual recreation of a Markov decision process that is visually visual mathematics, so to speak. And that's an example of reinforcement learning. Okay. Let's move on to the development framework. So you're probably asking yourself, okay, now that we've gone through supervised, unsupervised, and reinforcement learning, what languages do we use? So this was back from 2021, and it's still, it's not what you would think anymore. I would say from 2021 to now, it has changed quite a bit, in the sense that SQL is still very much used. We teach Java, HTML, CSS, which in my opinion are some of the worst languages to teach students, especially incoming into programming, because JavaScript, working with JavaScript within, it's an interpreted, but it's wrapped within an HTML framework. And then so you have to contend with that. Usually when you're developing JavaScript, you're developing within a wrapped framework. It means that you have to contend with two languages at the same time, HTML and JavaScript. So they aren't the powerhouses when it comes to machine learning. The big one is Python. Python. That's the big one. I will be using on occasion some Python examples, but I'm going to stick to my lectures for that. When we get to labs, we're going to be almost all in C++ and C. We'll be using the Arduino programming language, which is a compact, I'd call it simplified C. So that's probably the most apt description of what it is that we're going to be using, which is going to be simplified, which works well for us because, again, I'm not trying to create computer science majors. I'm trying to create machine learning specialists that have a broad capability to engage in different languages, from high to low, from high-level abstracted languages down to lower-level bare metal languages. So which ones do we use for machine learning? The big ones are going to be SQL, Python, and C. In the MLAS degree that we have, that is going to be, we teach students, we bring them up in JavaScript, and then we also teach them SQL, but then we spend a lot of time in Python at the undergrad level. I would say in the grad level, we primarily are in the Python C world. We don't cover a lot of SQL, and it doesn't exhibit itself in the machine learning and autonomous systems, but we do a lot of Python and C. So I will say though that if you have a knack, SQL is going to be unbelievably helpful for you to learn SQL, because I can tell you I can do things that other people can't do in terms of data cleansing, because I'm fluent in structured query language. So if you have that capability and you're fluent in SQL, in addition to Python, it's going to make your life so much easier in terms of being able to do things that others can't normally do or usually have to seek help with, to get some answers and insights into their data. The thing that I will say is I'm not super strong on C. So my for me, I grew up in the SQL Python world, and then and picked up JavaScript along the way, and then C is kind of the one that I'm weaker on. But we'll be fine. We'll get through what we need to get through for this course. But overall, these four are kind of my skill set. So you're in good hands in that regard. And we'll be in pretty good shape in terms of teaching the concepts, but then we'll be in really good shape with what we're going to be doing in our labs for our kids. Okay, so SQL, Python, JavaScript, just a little bit more. SQL, so if you're not familiar, SQL is a data access language. So when I say structured query language, it integrates real nice with, it integrates super clean with Python. It's a little more, it's not as clean with JavaScript, and it's pretty clean with C++. And the reason that SQL, Python, and C are really cool is, Python's your general purpose language. I like to think of it as something that you can use for just about anything. You can use it for GUI, although in my opinion, there's better languages for that. But you can use Python for front-end GUI development. Works just fine. I've done it. But I find that Python's great for back-end, general purpose back-end language and scientific programming. Because especially for machine learning, it's just such a robust and rich language in that regard. JavaScript's good, but it's better for it's more web-focused. It shines on the front end application development side of it. And then you've got C, which is great for low level, fault tolerant, fast, quick programs that you need to have. That's our bare metal language that we're going to be using. But what's nice about the Python route is that C integrates with Python really well. So there's what's called a Python implementation of Python that allows us to natively access C through Python. And then what's cool is SQL can natively access Python from within SQL. And vice versa. From Python, I can open a shell to SQL, execute commands, and then execute the SQL programming language, and then bring data back through what would be ODBC API calls. So there's a lot we can do in this area by just knowing these four languages. So I highly recommend that you have some. You're going to have some strengths. Mine are SQL, Python. Some people are going to be pure Python with a little bit of SQL, JavaScript, and C sprinkled in. Some people are going to be heavy on the JavaScript, where they know Node, they know React. They know JavaScript-based frameworks, and so there's some people that's what they specialize in, and there's some people that are C, and so that you'll have different flavors. But if you have some experience with all of these, you'll be in great shape. Okay, so there are different machine learning tools. There's a lot of different IDEs. There's VS Code, there's Spider, there's Anaconda, which is a wrapper for Spider. In VS Code, there's Orange, which is a data mining framework. SPSS, which is more of a proprietary framework that's put out by IBM. There's MATLAB, which is pretty cool too. It's useful, very widely used on the industry side. SPSS is heavy on the academic side, although I will say that Anaconda as a framework, as a machine learning wrapper framework, data science is right up there and gives us a lot of flexibility. I've used all of these. My favorite is the Anaconda world. That I've used SPSS on the academic research side, but I prefer the industry VS Code, Visual Studio kind of side of the house, where in Spider as well. So I spend a lot of time Usually my go-to is Spider when I'm doing Python development, and because it's a comfortable environment and I can do a lot in it. And of course native Python, right? It's scientific programming, a development interface for Python. So VS Code's really good too. It's a free one. Highly recommend it. Now, there's a lot of different machine learning frameworks out there. There's scikit-learn, PyTorch, NLTK for natural language processing. So that's Natural Language Toolkit. Scikit Multiflow. You got TensorFlow. You got Keras. There's a lot of you got ROS, which is Robotic Operating System. So there's a lot of different machine learning frameworks out there. We are going to be using, as far as the IDE, we're actually in this course going to be using the Arduino IDE. So we're going to download that in the lab this week and get that going, and then just do an equipment check and make sure everything's checking out. So we're using Arduino for our IDE, which is equivalent to the Spider and VS Code on the Python side. But what we're going to be using is what's called TinyML. So for one of our machine learning frameworks, because we're going to be focused on bare metal programming in this course, we don't have a lot of, we're working on smaller frameworks. We're working on smaller controllers that don't have a lot of ability to run abstracted, or they're not as good to run abstracted programming languages through an operating system. So in this case, we're going to be programming direct to the board using Arduino IDE, which is the simplified C. So that's what we're going to be using. But I do want to show this real quick, and that scikit-learn for Python is really, it's great for learning machine learning. And Google Colab is another one that we cover this in MLAS 800. We use Google Colab, and it's a online development environment that allows us to run all this stuff, scikit-learn, classification, regression, clustering, everything you can think of is going to be in here. And it is an amazing, Scikit is such an amazing resource. So I throw that out there for everyone because it is a wonderful resource, and you'll spend a lot of time in this world, especially on the industry side, doing a lot of data science work as well as machine learning work using Python. Okay. Here's a cheat sheet for you that will give you different ways to go about, like you've got regression, clustering, classification, dimensionality reduction, and there's these nice little, you can see here, like I've got all these K neighbors classifier. I have support vector, like I've got k-means, which is a clustering. And then let's see, I've got PCA on dimensionality reduction. Over here on the regression side, I've got ridge regressions. I've got ensemble regressors, which would be like random forests. So this is really cool because it's a nice little cheat sheet. It's a very famous one. It's specific to a lot of different algorithms, but the reason I say this is different tasks require different algorithms. You can't use one algorithm for everything. As an example, I can't use principal component analysis for every use case. I can use it as a go-to for my initial entry into clustering data, but I can't use, I mean you can, but it's not going to work as well. If I say, hey, I wanted to create a more complete predictive output for, let's say, a car driving, an autonomous, video image processing, I could probably use PCA, right? But I can actually get away with neural network doing a better job than a PCA does because I have trained data against a neural network versus untrained data on PCA. So that's why I say you want to. That's why a lot of times you'll see you'll do model evaluation and to determine whether the algorithm you picked matches best for what you're trying to do on the task, or um, um, or you'll reverse it. In other words, you'll say, hey, here's the task. This is the suite of algorithms that I think most are going to be best for me. You can back into it both ways, but either way, you got to do a model evaluation to determine, hey, this is the best model that I've got for the given task that I'm working on. So model evaluation is really important. Okay, so last on the talk here is for our lecture is we're going to be using TinyML, and so there's tinyml.org. It's nonprofit. They kind of bring everyone together on this idea of low power AI with a focus on edge computing, and that is by definition what we're working on in this course. So we're bare metal edge computing. And that's the focus of what it is that we're doing in 700. You did some edge computing using high level abstraction with the Adafruit on Python, which is an abstracted language, and that's okay for what we needed. It's a good intro, good primer. But for us, now that we're moving into kind of more industrialized settings, more operationalized settings, we're switching over to bare metal. Not that you can't do Python, but if I have small edge, cybernetic edge, wearable type computing environments, then I'm looking at something that has to be very fast and very efficient, and that's going to be a bare metal programming language. So we're going to be using TinyML in that regard because TinyML has its kind of roots in this area. Okay, that's all I've got for our lecture this week. Next up, head on over to the lab, and then we'll start to pull this SunFounder kit open and get it working. And we'll see you over there.